API. So until yesterday, we have seen the detecting changes in Sentinel-1 imagery part 1, detecting changes in Sentinel-1 imagery part 2. And today we'll see this detecting changes in Sentinel imagery part 3. So how you can, or I think you can do this at your end. Okay, let us see this. And after completing this detecting changes in Sentinel images, so we will go through the groundwater recharge estimation problem. So okay, this is a notebook on that, and then there is this awesome GEE, awesome Google Earth Engine. So any new concept you see in any tool, any programming or anything, you should try to search for awesome GitHub pages. So people maintain it like this, and this is maintained by Quisheng View. So we will see the Python API and associated Python repositories and these notebooks. So let us see how much we can do today. So we will start with detecting changes in Sentinel-1 imagery part 3, and okay. So first we will authenticate and initialize the Earth Engine library. So here is the Earth Engine API, the official Google Earth Engine Python API. And you should also see these other Python packages built for Google Earth Engine. So first is GE Map, which is a Python package for interactive mapping with Google Earth Engine, IPy leaflet, IPy widgets. Then we have GE Add, Google Earth Engine Batch, asset manager with add-ons, GE Up, simple command line interface for Google Earth Engine uploads, Carto EE, publication quality maps using Earth Engine and Cartopy, GE tools, set of working tools for working with Google Earth Engine and Python API. Then we have Landsat extract GE, NDVI to GIF, so creating seasonal NDVI composite GIFs. And we have EEMont, which is a Python package that extends Google Earth Engine Python API with pre-processing and post-processing tools. Hydra Floods REST EE, so package that aims to make plugging Earth Engine computations into downstream Python processing easier. WXE, Python interface between Earth Engine and Xarray for processing weather and climate data. And we have Task EE, so monitor your Earth Engine tasks and get notifications on your phone or computer. So these are, then we have these Earth Engine Pi notebooks, which are a collection of 360 plus Jupyter notebook examples for using Google Earth Engine with interactive mapping. And these are 300 plus examples for Earth Engine and GE Map Python package. So this is for Earth Engine Pi, the official Python API, and this is the GE Map package, which is developed by Kushangu. And then we have this TensorFlow notebook, so repository to place example notebooks for deep learning applications with TensorFlow and Earth Engine. So let us see how many are there in this. Okay, so we have Landsat QA CNN. So okay, anyways, we will first start with this one. Okay. So just like yesterday, we will import these data sets. That is the Sentinel-1 ground range detected images. So we will first import our libraries, and we will define this function chi to CDF, which calculates the chi-square cumulative distribution function for df degrees of freedom using the built-in incomplete gamma function, gamma inc. So and then we have this function det, which will compute the determinant of 2 cross 2 diagonal covariance matrix. And to make use of interactive graphics, we import the Folium package. Now, continuing from part 2, so this is the part 3, which is multi-temporal change detection. So in part 2, we discussed bitemporal change detection, that is change detection only between two time steps, right? And in this case, we turn our attention to multi-temporal case. So to get started, we obviously need a time series. So here is a fairly interesting one, region in South Yorkshire, England, where in November 2019, extensive flooding occurred along the River Don, just north of the city of Doncaster. So let us see where this location is. So we can just go to geojson.io. Okay, and okay. So this is the location, which is somewhere around North England near Sheffield. Okay, so you can see here this is the region Doncaster, uh, and extensive flooding occurred along the river Don, just north of the city of Doncaster. So just north of the city, along. So this is the river, I guess. Okay, so where extensive flooding happened. And okay, so just let's extract the coordinates from this GeoJSON dictionary, and we have the area of interest, which is geometry data structure. The image collection below covers the months of September 2019 through January 2020 at 6-day intervals. So we have this image collection, image collection, Copernicus S1, GRD float, and we filter bound. So that is just extract over this region, over this area, which is this box, and then you filter over the dates. So from 1st of September 2019 to 31st of January 2020, and also filter along the orbit properties pass. So select descending, relative orbit number start, which is 154, and map the image. So this is the key, and this is the value, and sort by dates. So then we have timestamp list. So you use the get info, and we'll see what are the times for which the data is available. So you can see 2nd of September, 8th September, 14th, 20th. So these are the passes, basically pass of the satellite. It will turn out to be convenient to work with a list rather than a collection. So we'll convert the collection to a list. And while we are at it, clip the images to our area of interest. So we can just say we can create a function clip image, and pass the argument as image, and just say e.image, you pass in the image, and dot clip AOI. So the collection, image collection is a data structure of Earth Engine, Google Earth Engine. We are transforming it to image list. We use the function toList, and the size, we have to pass the size, so which is given by image collection dot size. And this IM list, so when we, okay, let us break this. Okay, so let us just run this. Now, when we see the type of image list, so this is an list. So this is an Earth Engine list type. So we we can see that it is, and let us see what is the size of this. So let us check it. I hope this works. Doesn't work. Okay. So then you do list im. So this im list. So you say dot map clip image. So you clip over that area of interest. And okay, so it's not length of list. So you have to say im list dot length dot get info. So this will give you the number of images. So which is 26. And here is an RGB composite of the VV bands for 3 images in early November after conversion to decibels. Note that some changes, especially those due to flooding, already show up in this representation as colored images. So if you pass, so this function select VV, basically you just pass in this image current and you select this variable VV. So imlist.map select VV, because this will contain, we have not selected any particular variable, so this will contain, im list will contain all the variables, that is VV, VH, other variables that we were seeing yesterday. And then you get the location of the centroid, create a folium map object, and then you have your RGB images as, so e.image.rgb. So you first give the vv list.get 10, so the 10th, 11th, and 12th image, and you take log of 10 and multiply with 10. So 10 log 10 of this, all this RGB. And mp dot add ee layer. So what is this add e layer? This function must be defined here. Yeah. So mp dot add e layer. So where mp is your is basically your folium object. So that's why we are passing this as self, and it takes in as input the RGB images and the dictionary and the string RGB underscore composite. So you can see here that we are uh, we are creating this map ID dict, so which is creating this map ID dictionary e.image. You pass the e-image object, which is so e-image object for us will be okay. So yeah, the RGB images, and then we have the dictionary. Okay. So then you have the visualization parameters, and then you have the name. So you create the map ID dictionary, and you say folium dot raster layers dot tile layer, and to this map ID dictionary, you say dot URL fetch URL format, and then these are the attributes. So map data. So on the plots, we'll see that this map data and these things come, and the name, what is overlay control, add to self. So add to self basically means that it will add to the object. What is the object? MP. And mp dot add child folium dot layer control. Okay, so to control the layers, we will add the child. So you can see here that it's coming here, map data, copyright, Google Earth Engine, and this layer control has also come. So this is the RGB image of basically the from this list of images, which are from 1st of September 2019 to 31st of uh, January 2020. The 10th, 11th, and 12th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So starting from 26th of October, 26th of October, 1st of November, and 7th of November. So this is R, this is G, and this is B. Just a moment. Okay. So this is RG and this is B. And okay, so you can see that we can see here that okay, so these regions are flooded, right? You can see these specific regions which is corresponding to this river. It is, you can see the flooding here. Okay, so now we have a series of 26 synthetic aperture radar images, and for whatever reason would like to know where and when changes have taken place. So first reaction might be, what's the problem? Just apply the bitemporal method we developed in part 2 to each of the 25 time intervals. Well, one problem is the rate of false positives. If the bitemporal tests are statistically independent, then the probability of not getting a false positive over a series of length k is the product of not getting one in each of k minus 1 intervals. So which is 1 minus alpha raised to our k minus 1. And for our case, even for a small value of alpha, this gives a whopping 22.2% false positive rate. So if our alpha is 0.01, and we compute using this bitemporal bitemporal, or just compare two images, we have a high false positive rate. And actually things are a bit worse. Bitemporal tests are manifestly not independent, because consecutive tests have one image in common. The best one can say in the situation is alpha t less than k minus 1 alpha. And so how to proceed? Perhaps by being a bit less ambitious at first and asking a simpler question. Were there any changes at all over the interval? And if the answer is affirmative, we can worry about how many there were and when they occurred later. Let's formulate this question as follows. So an omnibus test for change. So we'll start again with a easier single polarization case. So for the series of VV intensity images acquired at times T1, T2 up to Tk, our null hypothesis is that at a given pixel position, there has been no change in the signal strength. So you assume that uh, for the null hypothesis is that there is no change. If your null hypothesis fails, then there is some change in the signal strengths AI. So where which is this SI image. So you square of S of AI and for the variable VV over the entire period, that is h naught equal to h naught is, so a1 equal to, so this is the null hypothesis h naught, which is a1 equal to a2 equal to up to ak equal to a. The alternate hypothesis is that there was at least one change over the interval. For the more mathematically inclined, this can be succinctly written as, so this is the alternate hypothesis h1 such that I comma j ai is not equal to aj. So there was at least one change that happened along that interval. And so the likelihood functions are the products of gamma functions. So the likelihood function of joint likelihood function of a1 up a2 up to ak is equal to the product of so the probability of si such that ai. Okay, so and you take a product from I equal to 1 up to k. So for all the different times, you find out the probability of Si such that Ai, and then open this probability as a gamma function. Okay, so when you do that, you get something like this equation, and for the L0 of A, you get something like this. And L1 is maximized for AI equal to Si, comma I equal to 1 to K, while L0 is maximized for A hat equal to sigma Si by K. So with a bit of simple algebra like our likelihood ratio test statistic. So this is our test statistic. Okay. So these are the different images, or these are at different times, right? What are the signal strengths, AI, A1, A2, A3 up to AK. So this is called as the omnibus test statistic. Note that for k equal to 2, we get bitemporal LRT, which is given by equation 2. So we saw minus 2 log QK. So this was what we were computing yesterday, if you remember. And for we can, so this is a generalized form of omnibus test statistic. And according to Wilks, it should be approximately chi-square distributed with k minus 1 degrees of freedom under h naught. So the input cell below, so this cell below, it evaluates the test statistic from equation 3.6 for a list of single polarization images. We prefer from now to use as default the equivalent number of looks 4.4 that we discussed at the end of part 1, rather than the actual number of looks m equal to 5, in the hope of getting a better agreement. So we take m equal to 4.4 here. This is the uh, this is the function which calculates the omnibus test statistic, and we have another function here, log function, uses which basically takes this image current and returns a log of current. So you convert this IM list to an E list. So you just say E list and you pass this IM list. So what is the length of this? What is the length of this image collection? It is k. It is given by IM list dot length. Now you take so you say k log k. You have to find out, so k into log k. So you say k dot multiply k dot log. So this k dot log becomes log of k, and this is into k. So k log k, and k log k equal to e dot image dot constant. So you convert it into a constant data type. It's no more a variable. It cannot be changed. And now you compute the sum of logs. So here, if you remember, we have sigma log of si. Okay, so you have to compute this term, sigma log of si. Okay, and log of sigma si. Okay, so this is the sum of logs, and this is the log sum. So how you will compute sum of logs? So e dot image collection. So and im list dot map log. So to this entire image collection, you take a log of it. Okay, so you take a log of it and uh, basically transform it into an image collection. And to this image collection, so now this is an image collection. You apply, so you use the function reduce, and the operator that we are using here is e dot reducer dot sum. Okay, so you can see here, you sum over log of si, and now you have to take log sum. So log, so you have to first take sum, and then you have to take log. So this becomes log sum, right? So again, this is e dot image collection im list dot reduce. So you first take this sum. So this one takes the sum, and then you do a log. So dot log. So this is log sum. And what you return is k log k dot add. So you add to it sum of logs. So you add the sum of logs to it. Dot subtract log sum dot multiply k. So k log k of log sum, k into log sum. And to this whole thing, okay, so this entire thing you multiply minus 2m. Okay, so then this gives you the test statistic minus 2 log qk. So let's see if this test statistic does indeed follow the chi-square distribution. First, we define a small polygon AOI sub over the Thorn Moors on the eastern side of the area of interest, for which we hope that there are few significant changes. So yeah, where is this location now? So you can see here, this is a big box, right? So here we select this smaller box, which is near this place Thorn. We expect that there are not that many changes here because this is farther away from like the river. And if you remember, we read that the flooding took place somewhere near Doncaster. And then we take, so we extract the coordinates, the area of interest, and you take the location, create a folium map object, and mp dot add e layer rgb images dot clip ay dot underscore sum. So you find this out. So for what is RGB images? RGB images is nothing but the 10th, 11th, and 12th. So here we had defined that. So e.image.rgb, the 10th, 11th, and 12th image, and you basically take a 10 log 10 of the actual values, and you select so you define this visualization parameters as in this dictionary, and you give it a name. Okay, so let us see this. So we are plotting the okay. Hmm. So here is a comparison for pixels in AOI sub with chi-square distribution with k minus 1 degrees of freedom. We choose the first 10 images in the series because we expect fewer changes in September or October than over the complete sequence k equal to 24, which extends into January. So now you see we take k equal to 10, and the histogram that we are taking is, so you take omnibus. So this is the omnibus function, and it is returning the test statistic. So omnibus, you pass VV list dot slice 0 to k, and dot reduce region e dot reducer. So you find out the histogram, fixed histogram of that region, right? And dot get constant dot get info. So this is your histogram. So a equal to np dot array hist, and so you x is the first column, y is the second column. Now we will plot this, and you see we are also plotting the chi-square distribution. So x and with k minus 1 degrees of freedom divided by 5, which is your m. So you see that it appears that Wilks theorem is again, so it's nicely following the chi-square distribution. So why not generate a change map for the full series? So good news is that now we have the overall false positive probability alpha under control, and here we set it to alpha equal to 0.01. So k is equal to 26, alpha is equal to 0.01, and our p value, it is equal to e dot image dot constant. So basically 1 minus chi-square distribution, and you find out with k minus 1 degrees of freedom and with VV list, and then you compute the C map, so which is p value dot multiply with 0, where p value is less than alpha, otherwise you multiply with 1, and make the no change pixels transparent. So so CMAP, you update mask, so where CMAP is greater than 0, and overlay it over onto the folium map. So you see we are plotting this CMAP here, mp dot add EE layer CMAP, and mp dot add child folium layer control. So let us see where all we get the changes. So you can see here that we have, so the palette is going from black to red, black corresponding to 0, red corresponding to 1. This is the change map. So there are plenty of changes, but hard to interpret considering the time span. And although we can see where changes took place, We know neither when they occurred nor their multiplicity. Also, there is a matter that we have glossed over up until now, and that is a question of scale. So, the number of looks plays an important role in all the formulae that we have discussed so far. And for the Sentinel-1 ground range detected imagery, so we first use m equal to 5, and now the enl equal to 4.4. So when we display a change map interactively, zoom factor determines the image pyramid level. So you can see here we have the zoom level here. So if you change the zoom to 10, you can see it. It basically shows a bigger map. Now if you change it to 4 or something, so you can see that it is showing even a bigger map that we cannot uh, clearly identify where our map actually is. So let us change this to, let's say, 12. The focus is on the centroid. Okay, so now you can see, we can clearly see this change map. So these are the locations where we had, where there was a flood uh, over the region. And so in order to see the changes correctly at all zoom levels, we can force Google Earth Engine to work at the nominal scale by reprojecting before displaying on the map. So you can see here CMap 10 meter equal to CMap dot reproject, and you reproject it to, okay. So if the calculations are not at the nominal scale of 10 meters, then the number of looks is effectively larger than ENL due to averaging involved in constructing higher pyramid levels. This effect can be seen in the output cell above. Okay. So here, yeah, this is the change map at 10 meters, and this is the actual change map. Okay. You will notice the output cell above, in the output cell above, the calculation at nominal scale, the blue pixels, now takes considerably longer to complete. Also, some red pixels are not completely covered by the blue ones. These changes are a spurious result of the falsified number of looks. So, nevertheless, for quick previewing purposes, we might prefer to do with the reprojection. And now coming to sequential omnibus test. So we have only done this omnibus, although we made the function omnibus, but we computed only the for uh, for the bivariate, or for the two images, the change detection. That's we computed this minus 2 log k. Now coming to the sequential omnibus test. So recalling the last remark at the end of part 2, let us now guess the omnibus LRT for dual polarization case. So from equation 3.5, replacing S with Ci, Si with Ci, sigma Si with absolute of sigma Ci, and k raised to our k with k raised to our 2k. So we get the test statistic as this one. And this is in fact a special case of more general omnibus test statistic, that is qk equal to k raised to power pk pi I ci. So multiply all the images, and then sigma ci raised to power k, whole thing raised to power m. So m is, the last time we used 5, here we are using as 4.4. So which holds for P cross P polarimetric covariance matrix images. For example, for the full dual polarization matrix or full 3 cross 3 quad pole matrices, but also for diagonal 2 cross 3 and 2 cross 2 and 3 cross 3 matrices. So which bring us to the heart of this tutorial. So we will now decompose the equation 3.7 into a product of likelihood ratio test, which will enable us to determine when changes occurred at each pixel location. Then we'll code a complete multi-temporal change detection algorithm on the Google Earth Engine Python API. So single polarization, rather than make a formal derivation, we will illustrate the decomposition on a series of k equal to 5 single polarization VV measurements. The omnibus test equation 3.5 for any change over the series from t equal to t1 to t5 is represented by this equation. So you can see here, so 5, we have k is equal to 5. So k is 5 here, 5 raised to power 5. Here we are taking p as 1, and product of all the 5 images, so s1, s2, s3, s4, s5, and divided by sum of uh, sigma I ci, so s1 plus s2 plus s3 plus s4 plus s5, and raised to power 5, and which is whole thing is raised to power m. So this is our q statistic. So for 5 images, if we accept the null hypothesis a1 equal to a2 equal to a3 equal to a4 equal to a5, which basically means that all the intensities were same, that is there is no change that has happened between the different dates, we are done and can move on to the next pixel. But suppose we have rejected the null hypothesis, that is there was at least one significant change. So in order to find it, we begin by testing the first of the 4 intervals. That's just the bitemporal test from part 2, where we can call it, let's call it R2 rather than Q2. So what is R2? So which is 2 raised to R2 S1 S2 divided by S1 plus S2 raised to R square whole raised to power m. Suppose we conclude now, if this with this test statistic, if our null hypothesis is true, right? So if h naught is true, then we would conclude that a1 equal to a2, that is no change happened. Now we don't need just another bitemporal test on the second interval. Instead, we can test on the hypothesis. So we can just test on the hypothesis h naught is equal to a h naught is a1 equal to a2 equal to a3 against h1 is a1 equal to a2 not equal to a3. So then this becomes our second hypothesis. And the alternate hypothesis thus is there was no change in the first interval and there was a change in the second interval. So the LRT is easy to derive, but let's go through it anyways. Let's not go through so much of detail. Now, so generalizing to a series of length k, the omnibus test statistic Qk may be factored into the product of LRTs Rj, which test for homogeneity in the measured reflectance signal up to and including time tj, assuming homogeneity up to time tj minus 1. So this your Qk, which is the test statistic, is a product of starting from j equal to 2 to k of product of Rj, where Rj is equal to j raised to j divided by j minus 1 raised to j minus 1, and s1 plus up to sj divided by s1 summation of s1 up to sj. The numerator is up to j minus 1, the denominator is up to j, and here you see we multiplied with j, take the whole thing raised to power m. And moreover, the test statistic Rj are stochastically independent under H naught. This can be shown analytically. See Conradson 2016 or page 4.405 of this textbook. But we'll show it here empirically by sampling test statistics Rj in the region AOI sub and examining the correlation matrix. So we will to sample the VV images, we will just say okay, so this is the j, so e dot number j, so this is just creating this constant number j. Get the factors in the expression for Rj. So these are all the factors we are getting. So what is our Sj? So VV list dot get j subtract minus 1. So j minus 1, you get the j minus 1 element and G fact. So the J fact we get is J dot pow dot power J. So J raised to power J divided by uh, J subtract minus 1. So this is J minus 1 raised to power J minus 1. So this is J factor, this component. Then we have the sum of J and uh, sum of J minus 1, right? So sum of J minus 1, this is sum of J. So sum of J basically becomes E dot image collection, we will list dot slice 0 comma J dot reduce E dot reducer dot sum. Okay. So over this, all these numbers from 0 to J, you sum, and then from 0 to J minus 1, you also compute the sum. And putting them together, you get Rj equal to sum of J minus 1. So sum of J minus 1 dot power. So you take the power, so this you raise it to J minus 1 power and multiply it with Sj and multiply it with J factorial. So multiply it with J factorial and divide by sum J raised to power J and whole thing raised to power 5. So this is your Rj. And then your sample, so your sample equal to Rj dot sample region equal to AOI underscore sub. So you extract that region, scale equal to 10, number of pixels 1000, seed equal to 123. And aggregate array, so you aggregate it in a variable name which is VV underscore sum and return this sample. So then what are our samples? So samples equal to E dot list dot sequence 2 to 8. So from sequence 2 to 8, you compute these samples. Calculate and display the correlation matrix. So you say np dot set print option precision equal to 2, suppress equal to true, and print np dot correlation coefficient samples dot get info. So we will run this later. Let us first run this one. So we will see what our samples dot get info dot shape is. Oh, this is a list. So let us see what is the length of this. So the length is 7. So we started from 2, went up to 8. So 2, 3, 4, 5, 6, 7, 8. Right? We took up to from 2 to 8. What did we take from 2 to 8? We sampled from the VV list, and VV list consists of 26 images. Those 26 images are from we saw that they are from a particular date to another particular date. Yeah, from 2nd of September to 2019 to 30th of January 2020. Okay, where were we? Yeah. So then you can get the print np dot correlation coefficient. So you can see that the off diagonal elements are mostly small. Okay, the not so small values can be attributed to sampling error or to the presence of some change pixels in the samples. Okay, and so dual polarization and an algorithm. So with our substitution trick, we can now write down the sequential test for the dual polarization or the bivariate image test series, which comes out to be this. So we have already seen this equation, and of course we have again to use the Wilks theorem to get the p-value. So we work with minus 2 log rj. So you compute minus 2 log rj and minus 2 log qk, which is summation of 2 to k minus 2 log rj. So the statistic 2 log minus 2 log rj is approximately chi squared distributed with 2 degrees of freedom. Similarly, minus 2 log qk is approximately chi-square distributed with 2 into k minus 1 degrees of freedom. So readers should satisfy themselves that these numbers are indeed correct, taking into account each measurement. Ci has two free parameters, S AVV and SBVH. So the sequential omnibus change detection algorithm is something like this, with a time series of k synthetic aperture radar images, C1, C2 up to Ck. You set L equal to k. Okay. Set S equal to Ck minus. So you just select some L images. So starting from k minus L plus 1 to k. So you will have you will have L images. Perform the omnibus test QL for any changes change over S. If no significant changes are found, stop. So successively test series S with R2, R3 until the first significant change is met for Rj, and set L equal to K minus J plus 1 and go to 2. So you change your L and then again go to 2. So if you have L equal to, so this is your L is equal to 2, 3, 4, 5. And thus if a change is found, the series is truncated up to the point of change and the testing procedure is repeated for the rest of the series. Take for example, a series of k equal to 5 images. Suppose there is one change in the second interval only, then the test sequences, so Q5 to R2, R3 and Q3. So then, okay, it's already 3 p.m. and this is big. Let us quickly complete this notebook. Yeah, so pre-calculating the p-value array. The following code cell performs map operations on the indices L and J, returning an array of p-values for all possible LRT statistics. For example, again for k equal to 5, the code calculates p-values for each Rj entry in the table 3.1. And before calculating each row, the time series C1, C2, C3, C4, C5 is sliced from k minus L plus 1 to k. The last entry of each row is simply the product of the other entries. The program actually operates on the logarithmic of the test statistics. So let us just run this. And you have the p-values. So the pre-calculated p-values, PVARR, are then scanned in nested iterations over indices I and J to determine the following thematic change maps. So you find out CMAP, SMAP, FMAP, and BMAP. So CMAP is the interval of the most recent change, one band byte values, so which lie between 0 to k minus 1. SMAP is the interval of the first change, so which is one band. The FMAP is the number of changes, one band byte value, so which also is from 0 to k minus 1. And BMAP is the changes in each interval. So the Boolean variable median is included in the code. Its purpose is to reduce the salt and pepper effect in no change regions, which is at least partly a consequence of the uniform distribution of the p-values under H0. If median is true, the p-values for each QL statistic are passed through a 5 cross 5 median filter before being compared with the significance threshold. Okay, so yeah, so these are the codes for filter I and filter J, computing CMAP, SMAP, FMAP, and BMAP. And yeah, let's just run this. Okay, so yeah, I think we will just end this here. I go through this notebook at your end later on after the class. If you have any questions, we can discuss more. And okay, so this is for the different days. You can see that the change map is computed. So these are the flooded regions for 7th of November 2019. for 13th of November 2019. This is for 19th of 2019. This is for the 25th of November. These are the flooded regions. Then you have 1st of December, 7th of December. Okay. Now the interpretation is somewhat easier. Negative definite cyan changes which appear between November 7 and November 13 correspond to decreases in intensity of VV and VH reflectance are due to widespread flooding. The positive definite changes red, which gradually overlay flooded areas in subsequent intervals, correspond to receding floodwaters. Okay. And without reliable ground truth, we can't really claim that change maps of the kind we have just generated will be helpful for flood damage assessment or control, but their potential usefulness is quite obvious. In the next and final part of the tutorial, we will have a look at some more possible applications of sequential change detection with SAR imagery using Google Earth Engine. So with that, I would close today's lecture.